Okay, so we have a repository here, the compendium, built by a great friend of mine, Whoopnopper. He used to work at Coinbase, but now I think he's doing private audits with a team. And he made a really nice list here of vulnerabilities. I'll link this repository on the YouTube video so you guys can check out. Let's see the first one here. We have transaction order dependence. Let's take a look at that. So transaction order dependence, commonly known as front running. Okay, what is the impact? So transaction order dependence can lead to several consequences, such as manipulation of contract state, resulting in unintended behavior or loss of fund, front-running attacks, where malicious actors exploit their transaction in order to gain an unfair advantage in decentralized applications such as decentralized exchanges or auctions. Let's take a look at a piece of code here, and it looks like we have a simple auction. We have the address for the highest bidder so far and the highest bid that was made at this point. Then we have a function that is to make the bid itself payable, requires a value. You need to send a value that is bigger than the highest bid. The highest bidder cannot be address 0. And then we refund the latest bidder, send him back his money, and we update for the new bidder and the new bid value. So in this example, the contract is vulnerable to TOD attacks. A malicious actor can monitor pending transactions and insert their own transactions with a higher gas price to ensure the transaction gets mined first. This allows the attacker to displace the original highest bidder, leading to a potential loss or manipulation of the outcomes of the auction. Remediation. Use a commit review scheme. This is very interesting. I recommend you guys doing some research into commit review. It's quite useful for these kind of situations. So let's go. Implement a commit review mechanism where users first submit a hashed version of their bid, commit, and later review the actual bid. This prevents attackers from knowing the bid amounts in order to review until the review stage. Batching process. Process multiple bids or actions in a C transaction, making it harder for attackers to manipulate the order. Random transaction order. Introduce a level of randomness in processing order transactions, making it more difficult for malicious actors to predict and manipulate the transaction order. Nice, okay. So let's take a look here at some of those mitigation steps. And we have a improved auction. Now we have a structure for the bid with the commitment and the deposit. So the idea here is I have a mapping of bids. I have the review end time, the highest bid, and the highest bidder. I commit the bid, once again payable. The value needs to be higher than the highest bid so far. The block stamp needs to be before the review time. And we update the bids for the message sender with the commitment and the value for this bid. Then we review the bid. So in this case, we check if the timestamp is already over the review stage, and then we require that the hashing of the bid plus the nonce gotta be equal the commitment. So otherwise you're gonna have an invalid bid review. Then you check if the bid is actually higher than the highest bid. You can do the whole process and send the money back. Really interesting. In this case, as we are creating a key per bid, someone cannot understand how much we're bidding, and two, they cannot understand. They cannot. Thus, is much harder for them to just front run us. Very interesting approach. Let's go to the next one. Once again, feel free to make any questions So second one is denial of service, unexpected revert. Let's take a look at this. So denial of service, this vulnerability arises when a function that's meant to execute a task returns an unexpected error due to exceptional conditioning or programming mistake, halting of execution of the smart contracts and returning the remaining gas. Impact. The impact of an expected revert vulnerability includes disrupt of a normal contract operation, rendering of the contract unusable, loss of user confidence in the contract, which may lead to reduced adoption or usage, and potential financial loss for contract owners or users if funds are locked due to the vulnerability. Now let's analyze how the following code for the simple action contract. So the contract below allows anyone to place a bid in order to become the current leader. Sorry, the contract below allows anyone to place a bid. In order to become the current leader, you have to place a bid higher than the previous leader, right? Simple. So here we have a the contract. Once again, we have the value for the bid, and here we are, sending back the old leader, and then we have here a message sender. Sorry, and the value. Okay, this code assumes that anyone placing a bid is an EOA, not a smart contract. With this assumption, line 10 will always send the amount of the highest bidder back to the previous leader. However, someone can spin up a smart contract without a receive or fallback function to receive Ether instead of an EOA to call the bid function to become the new leader. So, which means that I can create a smart contract and make the bid through the smart contract, and try to do an re-entrancy attack in here. This results in line 12 and 30, unable to be called, and then cementing the attacker contract as the leader, preventing full execution of the function by anyone else doing doing unexpected revert on transfer. So it's actually not a re-entrancy here, it's more like the problem here is that this could be a contract, and this contract could even like not receive Ether or something, and this will break everything. So cool. So to prevent this from happening, it's recommended to use the pull over push pattern. This means that the user can withdraw the value rather than having to send them, which also saves you a lot of gas doing that. Okay, we understood. So denial of service is the scope of making the contract stop working. Let's see one of denial of service, but now looking at block gas limit. So let's go. See if I'm still. Hey 00xdev, how's it going? We are going over a few vulnerabilities here. Feel free to open your mic and talk to us, okay? So what we're gonna see now is a denial of service based on the block gas limit. So at this time of the post, the block gas limit for the Ethereum main network is about 30 million. A transaction that consumes more gas than that cannot be mined at all, which can lead to a denial of service. This vulnerability exists when excessive amount of gas is used to execute a transaction, causing it to fail due to reaching the maximum gas limit, effectively rendering the contract unusable and causing a denial of service for other users. Okay, so let's take a good look at the impacts. We have two forms of this vulnerability: gas limit DOS, unbounded contract operation, and block stuffing. And also we have this block stuffing. Let's take a look at this one. Gas limit DOS, unbounded contract operation. This DOS occurs when someone tries to arbitrarily inflate the amount of gas without bounds to exceed the block gas limit and render the function uncallable. Block stuffing DOS. This DOS occurs when an attacker fills a block with a large number of transactions, which may be invalid or have a low gas fee, forcing the network to include the invalid transaction and congest the network. As long as those transactions specify a generous amount of gas price, rational miners will include the attacker's transactions at the block. Okay, so let's take a look at the unbounded contract operation example. So consider a simple contract that stores a limit that stores a list of addresses and allow users to remove their addresses from the list. Okay, so we have a contract version 8. We have a contract address list, then an array of addresses, public one, then an external function to add an address to the array, and then a function to loop through the array and remove the last one. Okay. In this example, the function iterates through entire array address array. If it grows too large, the gas required to execute the function may exceed the block gas limit, rendering it unusable and causing a DOS. So if I come here and I just start pushing 1 million, things in the array, what's going to happen is I'm going to create a really big loop here, and that will lead to a block gas limit error. Okay. The remediation will be to using mapping instead of array. In this case, where the data storage and the retrieval are primary requirements, consider using mapping instead of arrays to reduce gas costs and improve performances. Limit iterations, limit the iterations in the loops, and consider breaking down large operations into smaller transactions that can be executed separately. Batch transactions. Processing multiple items in a single transaction or implementing a mechanism that allows users to process items in smaller chunks. Okay, so here we have a better list. So in this case, we have a mapping for the address, so it will always be a lookup straight into the address. We're gonna need to iterate that. The add address will never feed another variable. It will always be, adding the same value to the mapping. And the remove address can happen with a delete. So this will make this value go to false once again. So really interesting, very nice. Let's go to the next one. Re-entrancy simple. We're gonna get into these different kinds of re-entrancies, and there's a few that are complicated, so I'm going to skip those to the next lesson, but we're going to stay doing this anyway. So let's talk about re-entrancy. So this vulnerability is introduced when an external call is performed through another contract, as it can lead to a change in control flow and changes into the data of the calling function that were not intended. So the way it works is contract A, check balance, send funds, update balance. Contract B has a fallback function, and every time this fallback function is called, he's calling the function on contract A again. So it's basically creating a loop in the contract, never changing the context, which means that the balance was actually never updated because we're still under the first call. So this is really interesting. What is the impact? With a re-entrance, someone can simply drain your contract, or change the state, in a very considerable way. Let's take a look at one example here. So this code allows users to withdraw funds from their balance. Where in the code you could see a means for an attacker to overtake the execution logic and perform the malicious actions. So let's try to find it. So we have here a contract, and we have a function amount, and I can see that the problem here is this line 7, because we're calling the sender with the value, but with no function. So the sender, if the sender is a contract, automatically he's gonna go for the fallback function, and he's gonna call withdraw again, and this will happen until the contract is completely drained out, because only in the end we are doing the if to update the actual balance. The line, we actually never got to that line. So yeah, that's interesting. So Hey, Carly dog, how's it going, man? So you didn't bought the mic, did you? Get the mic, man. Um, there are two things. So today we are going over a few vulnerabilities. Work from our friend Obheda, and yeah, right now we're going over re-entrancies. We just saw a simple one. Hey, and with this re-entrancy, we have a call that is performed for a contract or EOA, performing withdrawal functions to receive funds. So what we're seeing here on line 7. And after the funds are received, a state change balance occurs. So this goes against the check effects interactions pattern that would only do that, that would first change the state and then send the money. Um, so if an attacker calls the withdrawal from a smart contract with a fallback function, a fallback would execute with any arbitrary code given sufficient gas. This is important. So if whenever you're iterating through a fallback function, you need to be constantly aware of how much balance still in the contract so you don't get an overflow problem, and how much gas you can still use. So you have the gas left operator on Ethereum to do that. Who controls the execution logic then? The attacker contract can include a call to the withdrawal function again within the fallback function, thereby controlling the execution logic and performing the withdrawal repeatedly until the contract is empty. Do the balances of message sender checking or do the check for the balance occurring before the transfer, the attacker can continue the loop and he enter the withdrawal function without ever updating their balance in the contract to drain all available funds. Okay, so let's go. And now, what is the remediation for that? Okay, so the remediation for that would be to use the checks effects interaction pattern, where all the state changes happen before interaction with external contract. So you can see here that the change that we added is we changed the value before. So now whenever he calls again into this contract, he's gonna be stopped by this if. So this if is now it's not valid anymore because the balance was updated even before the call. And it's interesting here because sometimes you're gonna see that happen the right way, but the call here is not being checked for the return. In this case, we are checking, making sure everything, the transfer happened and everything went through smoothly. So yeah, this is very nice. I'm gonna jump these two kinds of cost contract entrances because I wanna cover them in a different session because they require a little bit more focus. And I'm gonna go for self-destruct and we're gonna keep on going from there. Okay. Improper checks for an EOA. So what is an EOA? An EOA means an externally owned account. Okay, so a wallet. So here we're talking about how the opcode exit code size is used in Ethereum to determine the size of the Ethereum account's code. And just to give it a little bit of context here, an account with no code is a wallet, and an account with some code is a smart contract. If the size of the color code is greater than 0, then according to its zip code size, is assumed to be a contract. If not, then it's considered an EOA. However, relying on that can lead to problems and expected behavior. Because in some scenarios, exit code size will return 0 for a smart contract. Okay, so what are the scenarios that will return 0? A contract constructor. This is a classic one. So imagine that you write into the exploit file and all the code for the exploit happens in the constructor, basically that smart contract will be considered an EOA instead of a contract, because it's still gonna be, if you're able to execute the exploit inside the constructor, all the code size is still gonna be zero. So be careful with that. If someone calls a function, EOA will return zero. Um, so this is a very interesting one. So an address where a contract will be created. So what people do also to play to full easy code size is pre-calculate their next address for the exploit. So they have the exploit contract, they use the same nonce and use create two, and they get the address that will be deployed. With that, they are able to use the address. So the address at that point is not a smart contract yet. So it work for the check. But once everything's set in place, he just runs the code, then now he's going to deploy on that address. Now that address is a contract and can do whatever a contract can do in there. Another situation that happens is that people will create contracts, then destroy them. So I can do some. I can create a contract, get an address, destroy it, use that address, and create the contract again. Uh, um, so an address that was a contract at some point, meaning that it had code size. If the contract goes through self-destruction, then code size will go back to zero. So it's important to understand this, the impact of this. Let's take a look at some example here. So this is a classical function you're gonna see in some places, and people decided to implement it in different ways. But pretty much is the function is smart contract. You pass in an address, and the address will be checked to see if this is a smart contract or what. And we can see the assembly here. So we declare a variable for the size, and then the assembly block we have size equals exit code size with the address. So I pass in the address, I have the exit code size with the address, and the idea here is, okay, if this address is a contract, this will be bigger than zero, and this will return false. um yeah, okay, but what happens is this is not safe. Okay, yeah, this is not safe. Let's keep on reading. In this example, the EOA function checks for the input address of an EOA. If code size is zero, then the method is vulnerable because it could return false positives for contract with empty codes. So pretty much he's saying that this method, you shouldn't be using this because I can still use a contract and get a zero true here. Um, Remediation. To actually identify EOAs in contract, you should use address code.length method provided by Solidity, or the start call, which is more secure and reliable. So we have the start call. In this remediation, the EasyOA function uses a static call to check if the input address is an EOA. This method returns true if the call is unsuccessful and the result length is zero. This approach is more secure than relying on the exit code size. Cool. So we learned something today. I thought that we didn't have any possible solutions for the easy OA thing. I'm sure you're also gonna find problems with this implementation because I know that this is not a solved thing, on Ethereum. And of course, the idea of this compendium, it was to go on it daily, but let's just speed run it. And maybe we can come here and maybe design a few CTFs based on each one of these problems. Let's go for improper access control. So, access control vulnerabilities in Solidity happen when a smart contract does not properly restrict access, functions, or data. This can lead to unauthorized action being performed by malicious users or other contracts, compromising the contract security, integrity. Common access control issues including proper use of function visibility, missing restrictions, and reliance on tx.origin. So let's take a look at this guy. So the impact of access control vulnerabilities includes unauthorized access to sensitive data or functions, potentially leading to theft of funds or manipulation of contract state. Loss of user confidence in the contract, which may lead to a reduced adoption or usage. Damage to the reputation of the contract creator or associated organizations. So basically, we're talking about forgetting to use the only owner, using, setting a function that should be public to internal to public, enabling overriding in the wrong places. So let's take a look at the wrong list, and then let's take a look at the fixed one. So we have this improved address list, and we have a mapping for address and boolean, mapping for addresses. Then I have a add addresses function, remove address function. Same thing we saw before. Now the remediation is, oh, I think we found a little bit of a problem. Let me report that to Whoop. Whoop. Someone is sending me messages. Oh, nice. The CEO of Optimism Airdrop is talking to me. I gotta get this one right. Let me talk with you. Okay, but it's not really a lesson, but it's okay. Let's go back and let's take a look at just see if this contract here is yes. So once again, you see we have the only owner, we're using the only owner, so this vulnerability specifically is about not forgetting to control your access properly, okay? Now let's go back. And let's go to the next one, which is encrypted private data, like this one. So encrypted private data. Sensitive data stored with a blockchain without encryption can be a critical security issue. Due to the transparent nature of the blockchain, all data stored within contracts, including private variables, can be accessed by anyone with access to the network. This can lead to the exposure of sensitive data, undermining user privacy and potentially compromising the security of the smart contract. Okay, so the idea here is that imagine this. I have this variable here, users, and this variable holds a mapping of addresses to structures. I have a structure for the name and a structure for the social security number, which is private, you shouldn't share, right? So someone that would be maybe a little bit naive and write this smart contract and writes this variable as private may think that, okay, this is safe information, nobody will be able to read it, right? Well, there's several problems here. First one is you calling this function at some point, and if this contract is verified, most likely your transaction information will be right in there they will be available, so your name and social number. But not only that, it's also possible to work with memory storage, to work with the storage of the smart contract to read this information. So let's take a look on how the storage approach works. In this example, the contract stores usernames and social securities in a private mapping. Despite the mapping being marked as private, this data can still be accessible by anyone who can interact with the contract storage or analyze the blockchain. Accessing private data on-chain is possible by interacting with the contract storage. For example, using a tool like the Ethereum JSON RPC, pretty much talking about the terminal, so you send some requests to the Ethereum server node, right? Let's do a demonstration here. So to read private storage variables using Ethereum, you can use the if get storage at method. This method allows you to query the value of a storage in a slot of a specific contract. So just to make this a little bit, maybe a little bit more concrete, we're literally talking about, I think I don't have that here now, but let me check. Cat code, maybe if I do if, or maybe serial. So we're literally talking about calling the node, so we can do that through the terminal, we can use a client, so we're gonna call the method called if get storage f. With this method, we're gonna be able to read whatever is inside that storage, So let's take a look on how this works, okay? This method allows you to query the value of a storage slot of a specific contract. Keep in mind that although storage variables are marked as private in Solidity code, they're still accessible in the blockchain. 1. Identity of the contract address. Find the address of the contract whose private storage variable you want to read. So let's say you have this guy, this is your address. Check which storage slot do you want to access. The storage slot is determined by the position of the variable in the contract. For mapping, is a little bit more complex. So for mapping, what happens is we're gonna do a k-check of the key of the mapping. So let's say in that case could be the user address and the index and the value. So the index actually, sorry. So with that, we're gonna have the information. Sorry guys. With that, we're gonna have the information to read the mapping. Okay, so if you refer to read private variables, read private mapping, or read private variables with Solidity, there's a really good article. But it's not really an article, it's more like something by Solidity by example that explains exactly how all of these are calculated. I'm also going to drop that in the link in the video description. Okay, let's go back. Okay, so we use the method if get storage at against the RPC to read a certain storage slot from a smart contract. And we can kind of see here a small script that was done just to do that. So you see we have the contract, we have the user address. Then what we do is we calculate the storage doing a k-check, a SHA-tree of the user address. We're adding the padding of 64 zeros just so it's compatible with the way the node expects the information. And then we code into hex. So this is pretty much our slot position, and we can just read it here. We're gonna get the information even though it was marked as private. And I guess maybe one thing you need to understand is you're gonna get the result encoded as hex, so you're gonna need to decode it as it's explained here. Okay, so let's talk about some remediation. So just store less thing if you can in the smart contract. Whatever is sensitive, it's gotta be encrypted, and you can make use of some zero knowledge technology to do private transactions, on some commit review scheme. Um, and now we have here a improved user info. Once again, an array of, now I don't have user names anymore. I have user hashes. So I have one hash for each user. That would be much more complicated to calculate. Uh, um, and I will never know, that this information because it's pretty much hashed. Awesome. Let's go to control delegate call. This is probably the last one I'm covering here because I'm gonna leave the juiciest ones. So signature malleability would be probably one full video just for that. Price oracle manipulation can also be one full video just for that. And I'm gonna talk also, so I'm gonna get 5, 6, 12, and 13. We still have to cover those probably in the next session because those require more time. So let's talk about control delegate calls. So a control delegate call vulnerability in Solidity occurs when a contract uses the delegate call code in an unsafe manner, allowing on a contract to control the target contract address or function to be called. This can lead to unauthorized execution of functions, manipulation of contract state, or even complete takeover of the contract. Delegate call is a low level of code that allows a contract to call another contract function using his own storage context. The callee contract can read and write to the caller's contract storage. So this is very important to understand is when I'm using a delegate call, it's like I'm importing code, but I'm still messing with my storage. So whatever happens inside that code, still messing up with my storage. So if I'm just replacing the owner or maybe changing some balance, everything happens like it was my code. So be very smart when dealing with delegate calls. So the impact is, unauthorized function execution, theft of funds, unintended state, and consequences. You can also pretty much control the whole code. So you want to have like this complete control takeover, contract takeover, which is pretty much the worst possible thing, and loss of user confidence, of course. So let's take a look at how a contract could be considered. Let's say that this contract has a 100 ether, so it's constantly receiving ether, and it has a execute function that will get a contract. So here I can specify any contract, and I can say and I can format a call and bytes data and call data, raw call data. So I just calculate the function signature with all the parameters that I may need and everything. So I send it here, and when I do this, what happens is the execution function accepts a contract address as data input parameters and data as input parameters and performs a delegate call to the target. However, since there are no access control or validation of the target and data, an attacker can exploit this vulnerability to call any function in the contract, including those that were not meant to be called. So imagine that I have a withdrawal on the owner function here that will take all the money. I could change the owner and I could withdraw the money just from this call. Let's take a look at the attacker contract. So that's very interesting. So look, constructor payable message sender. So he's pretty much setting a address of the message sender to be the owner. Cool. So some attack function, and there's still the ether function. Okay. Now it's important for us to understand that when we say message.sender here, the sender still ourselves. because we used delegated calls here, what happens is that all the context is being delegated. So who called it, whatever was the balance, whatever gas was spent, so me, I'm still the owner here, you know. So yeah, I think this is it. I can be wrong. Payable message sender. Who will deploy this contract? Yeah, it's the fucking owner. And now the owner transfer ether. Address this balance. Yeah, look. So we are sending to me all the ether in this contract, which may seem okay, but this contract has no ether. Yeah, but the other contract has ether and is importing all the code, So he's explaining the attacker sends 100 ether to delegate call proxy contract. Attacker deploys contract to the network. Attacker crafts a malicious payload to steal ether function to call the steal ether function of the contract attacker. Of the attacker contract using the delegate call. This can be done by encoding the function signature. The attacker calls the execute function of the delegated call proxy contract, passing the address of the attacker contract and the malicious payload, so the bytecode and so the target and the data here. Now the contract, the delegate call proxy contract performs a delegate call to the attacker contract executing the steal ether function. Now the 100 ether that was in the contract will go to the attacker. So you see, this is really a tricky one. This is a tricky one. Let's take a look at the remediation steps. So first thing, use some access control. So make sure only certain addresses can be called. So you have a list of whitelisted smart contracts that are safe for you to interact with. Same thing here is talking about, he could be talking about specifying who can call certain functions, and in the validate target, he's talking about adding contracts to a whitelist, so their trust. Always avoid delegate calls when possible, consider using, other things, like interfaces. Just avoid low-level calls as much as you can. So to remediate the revised delegate call proxy contract, we can access control mechanisms to restrict. We can add access control mechanisms to restrict who can call the executive function. One way to do this is by using the ownable pattern, as mentioned above, which allows you to only the owner can delegate calls. So we would have the same thing, but now only the owner. Today, something like that will still return a medium, I think, on C4 or a low or something, because the thing here is that they're gonna accuse it of centralization because the owner can still call a malicious contract and etc. So yeah, that's very interesting. Let me see if there's any, because I say that I'm gonna be looking at those after. I'm gonna see if there's any. I'm gonna see. 1 second. Hey Carly, how's it going? I'm gonna see how many, if there's any one of these that I wanna go back into. No, I think this is it for today. So for this session, we're gonna have another session soon. Thanks, Carly, for joining. And yeah, this is it. I'm stopping the recording. See you guys.